Saxon Advanced Mathematics, lesson 101. We're going back into the archives a little bit for this lesson. We're going to talk about 3x3 determinants. Ooh, what is that? That is when we have a matrix that looks like this, and we use that to solve problems. All right. Well, in order to figure this out, we have to refresh our memory about Cramer's rule. That was lesson 74. Like, that was a long time ago. So let's refresh that. The idea that Cramer, who was a dude, he had other people who were working on this situation with him. His name was Gabriel Cramer. He was Swiss, and he published this idea in 1750, although people who were doing research on it hundreds of years back from there. German guys, Scottish guys, Swiss guys, an English guy, they were all working on this idea of how can we figure out ways to solve systems of equations besides substitution and elimination, because there's a number of steps. It takes a while. So what if we came up with a formula or a process that could shortcut us right to the answer? I admire their aim, because I think it's always a good idea. Like, let's make this easy, right? We don't have to do it hard just because we know how to do it hard. So they came up with this idea. So they first took a system of equations and they put in coefficient letters. Okay, and it's always a little bit off-putting, because what they did was they went A, B, C, D, and then E and F on the other side of the equal signs. I used to always want to go A, B, C, D, E, F, but that's not right. A, B, C, D, E, F. And then what they said is, let's solve it by elimination. So let's eliminate the y's. So we're going to multiply this side by let's put the minus on the bottom. This one will multiply by D, right? So then this will cancel, and then this one will multiply by minus B. All right, so they'll get the minus sign down there. So they multiply through, and they get A dx plus B dy equals ED, right? I'm just distributing that D across. C dx minus B dy, my marker is skipping at the top of the page, equals minus BF. I'm keeping things mostly alphabetical. I guess I messed that up. Now we add. Those cancel. We get A dx plus C dx equals, and I'm going to fix that alphabetical problem, DE minus BF. Now we want to set this up so it's x equals. So we'll factor out the x. It's AD minus CD. Second, I feel like I made a mistake in here. Oh, yes, this should be a minus. So that should be a minus. It would be ADX minus, oh, this should be a B. Sorry if I confused you. I multiplied that incorrectly. Minus B times CX is minus CBX. I could have gone alphabetical. But it's, so now it's AD, and this should be CB minus. Okay, now I'm back on track. CB equals DE minus BF. Okay, I feel good about it. Now what we want to do is we want to divide away this part. And again, I'm just going to fix this. I keep messing up my alphabetical, but that's fine. AD minus BC. This all cancels, and we get this as a shortcut way to get to a value for x. But then the boys took it even further. It was all boys at this time. they said, what if we wrote this as a matrix, right? What if we took the original values up here and we made matrices that would allow us to calculate this? How would we do that? Okay, DE minus BF. How do you write that in a matrix? Well, you want to multiply, and this is the order that that mathematicians use it. So we're kind of going slightly alphabetical, but you'll see how it works in just a minute. If we do this, we multiply this first in a matrix, right? We go from Seattle to Miami, that, and then we subtract B times F, right? That's how you solve this. You say E times D minus B times F, or whatever order you want the letters in, right? That is how we could write this pattern of coefficients in matrix style. And then for the denominator, we do the same thing. And we would put A times D, right, minus B and C. And this gives us the same thing back, right? Because it's AD minus C times B. Again, the order doesn't matter, but look at how we get the same thing. DE minus BF. That turned out the same. This is over. AD, that's this, minus BC or CB. So what this proves is that instead of using all of these cumbersome letters, we can rewrite the value for X as two matrices, and we can use those determinants, the answers to the matrix, to come up with our specific answer for our value of X. Okay, interesting. What that means is that you can memorize these formulas, and Y works the same way, right? We want to solve for Y as well. I'm just focusing on the X right now because everything in the Y story works exactly the same. So what we came up with is the idea that if you wanted to memorize this pattern, then you would have those answers available to you and you wouldn't have to go through all of this. And when they looked like this, it was fairly easy to think, okay, well, maybe we can actually memorize this. Let me just show you how we would what the Y would look like. We would do the same thing. We would go all the way back to the beginning, but this time we would eliminate the X's and solve for the Y. And then we would do this same process of solving for the Y and then translating that into matrices. I'm going to show you what the matrices look like. If you want to see this process in detail, go back to lesson 74. That's the lesson that this is coming from. Okay, so if we did all that work, we would come down to a matrix for Y that looks like this. Okay, and again, that would translate directly into what we had here. I'm not going to show that now. All right, now I remember telling you back in this day, you can just memorize them cold, but you can also see some really cool patterns. The denominators are the same. And these, if you will note, they're exactly the same for X and Y, and they come from the four coefficients that relate to the X and the Y up here, right? A over C, B over D. A over C, B over D, A over C, B over D. So the denominators are the coefficients from the variables. Right? This rule we're going to take with us into today's work. But let's look at the pattern in the numerators now, because that's where there are some differences, right? Both X and Y have the very same denominator, and it comes from the 4 variables. But now let's look what's happening in the numerator. Both of them, what I want you to do is I want you to think of this is the X column and this is the Y column. That matches up to what we have here. Notice that for the X variable, we went to the Y column and we filled in the Y variables, right? B and D are the Y variables. I'm going to circle them in blue to show you that they're showing up again right here, B and D. But look at this. In the X column, when we're looking at the formula for X, we don't put the variables for X in there. We go to the other side of the equation and bring in the E and the F. So in the column that matches to the variable we're trying to calculate, we don't put in the variable, we put in the other side. And look, the same thing is happening down here for the Y's. We go to the X column and we put in the variables that match for the X, there and there. And then in the Y column, when we're trying to calculate the Y, we don't put in the Y values. That's when we go over here and again, use the E and the F. So there is a pattern to this that helps us memorize it, but it's going to be super useful today when we start talking about 3x3s, because we don't want to go through all of this for our 3x3s. It's nutty. So we're going to remember this pattern, and I'm trying to put it into words. It's a difficult concept to write out, but you can see it quite plainly when I show that. The denominator is made from, let me see what words are here. The coefficients on the variables. The X, Y, and as we will soon see, the Z. And it is the same for all the variables. We saw back there that X and Y, here, let me just rip this page out so I can show you. X and Y have the very same denominators. That is going to be true today. The numerators follow this interesting pattern that we talked about here with the reds and the blues, and I'm going to attempt to put that into words. So to calculate the numerators, you put the other variables, because we're always solving for one of the variables, right? So you put them into their columns, just as we showed here, right? When you're solving for the X, you put the Y into its column. When you're solving for the Y, you put the X into its column. But you put the constant, or as I like to call them, the plain numbers, no variables attached, into the place of the variable you are solving. Okay? I'm solving for X, so I put the Y letters into place, and then when I get to the X column for the X that I'm solving for, then I put in the quote-unquote plain numbers or the constants that are over on the other side, all right? The reason I'm making such a big deal out of explaining this to you for our 2 by 2 matrices is that we're now going to go up to 3 by 3, and we are definitely going to want to use this rule because we do not want to memorize something like this for a 3-parter. I'm going to show it to you in just a minute. We're going to let John do the heavy lifting on proving to us how these matrices work, and then we're going to use these rules that our good friend Kramer developed for matrix solutions to a system of equations. I'm not going to write all that out. But we can use these rules to make it easier for us. Now, see how I started with this and I solved it to show you that this was correct and then we could jump from here to the matrix? Let me show you what that looks like when John does it in lesson 101. Don't hurt yourself looking. Look, he writes the system of equation with subscripts this time, but look, all 3 of them. And then this is what the formula looks like. I don't want you to memorize that. I want you to use this simple rule that we've worked out. So now what we're going to do is with a 3 by 3 system, we're going to write out the value, the matrix that you can solve. It'll be the equivalent of this and this. And like I said, we're going to use these rules to develop it. So what does that look like? Well, John switches from using the, let me show you. Here he went with A, B, C, D, E, F. You can also write this as A1 plus B1 equals K1 and A2 plus B2 equals K2. It's another way to do it. John's going to use this system instead of the A, B, C, D, E, F. But it's the same way, right? A1, B1, A2, B2, and then the constants are K1 and K2. So we're going to use this. It's just another style of writing out a system of equations with all letters instead of numbers. So he's switching styles, but the process is the same, all right? So imagine that we have A1x plus B1y plus C1z equals K1, all right? So there's our x, y, and z. There's the A, B, C, which is similar to what we had here, except we added the C. And then our answer is K, just like before. Now we have to do it a second time to represent the second equation. And then a third one. 3 variables, we need 3 equations. A3x plus B, this should be a y, sorry, equals plus C3z equals K3. Let's pray I got all of this right. This is when we're actually getting into the 3 by 3 determinants. Okay, so we've switched gears from our 2 by 2 application to now we're doing our 3 by 3. This is the system that we'll use to develop it. So how do we calculate the formula to solve for x? Okay, we know it's going to be a big matrix up here, and we know it's going to be a big matrix down here, and then we're going to do a y as well. So let's just set that up at the same time. Okay, let's remember our rules. For the denominator, we make it from the coefficients on the variables. What does that mean? Oh yeah, A, B, C, D, A, B, C, D. So what we'll do for this 3 by 3 is it's pretty straightforward, A1, B1, C1, A2, B2, C2, A3, B3, C3, right? So we're just going across and we're picking up the abstracted coefficients, right? We turned them into weird little letters and subscripts, but we're just picking those out. We're gonna do these with numbers, PS, in just a minute. We know it's the same down here. The denominators are always the same. Okay, like I said, we're gonna put numbers in and we're gonna show you how to solve these in just a minute. John and I are gonna help you out. Okay, so now let's look at the numerators. Those are the tricky ones. We're gonna have an A column, a B column. Oh no, we don't wanna say A, B, and C. We wanna see X, Y, and Z. All right, so in the X column, we will not put the X values in here. We'll put these. So this will become K1, K2, and K3. But then the X's and the Z's will go ahead and fill it, or the Y's and the Z's rather. The Y's, this will be B1, B2, B3, and the Z's are C1, C2, C3. Let me double check and make sure I did not do anything ridiculous. Yep, the K's are in the first place. The B's. These are just our column headings. They're not part of the matrix, okay? Let me puff those. That's just to help us keep track of what we're doing. This is the matrix. And then solving that, we would get a fraction, and then that would be our answer. Okay, now let's deal with these renegade Y's. Again, what I like to do is go first to the column that matches what you're solving for, because that's the tricky one. We're solving for Y, so in the Y column, we want to put in the constants. K1, K2, K3. Then in the X column, we'll put in the X coefficients, A1, A2, A3. And then in the Z column, we'll put in the Z coefficients. Does that make sense? We can't solve it any more than this until we get numbers, but we'll eventually be able to reduce each of these numerators and denominators to a number, and then we'll put them over here, and we will have actual values for X and Y. Crazy, right? Okay, let's do one. Let's actually put in some numbers and see if we can solve using this pattern. Again, I don't want you to memorize this. What I want you to memorize are the rules that we use for creating this. This is nothing you want to jam into your head, all right? Okay, carrying on. Example 101.1. Here we go. Use Kramer's rule to solve for X, Y, and Z. So then we're given a system of equations. 2x plus, now what I like to do is give everything a coefficient. In the book, this is just shown as plus y, but I want that 1 in there because I don't want to have to think about it every time I go to lift that coefficient to put it in one of the matrices. Plus 2z equals 7. One of the point John makes, and honestly, I don't know that I've ever seen him make this before. He has a little box and it says, it is easy to make numerical mistakes when using determinants to solve 3x3 equations manually, meaning not a computer. Work these problems with 1 or 2 partners. Oh, I think that is so smart because you'll catch each other's silly little mistakes. And I wish that math could be more of a social enterprise because it is really healthy to have other people working and catching mistakes with each other. That's why I like to teach in person, is because when I'm teaching here in my dining room without you, you don't catch my silly little mistakes, and that's frustrating. So if you do have a friend or a student that you, or a fellow student that you can work with, do it. Okay, the second one, again, I'm copying what John has, but I'm inserting coefficients of 1. So that'll help me fill in my matrices. And then the last one, 3x minus 1y plus 2z equals 16. Okay, so first we will solve for x. No, I lied. First what we'll do is solve for the denominator, because that will be the same for everybody. Okay, to calculate the denominator, we use the coefficients off the x and the y and the z, right? It's made from the coefficients on the variables. The variables are x, y, and z. It's the same for all the variables. So once we calculate this, we're halfway done to everybody's calculation. All right, so we're gonna put in 2, 1, 2, 1, 1, minus 1. Now you can see why the ones are kind of handy because I can copy them without having to think at all. 3, minus 1, 2. Okay, so there is a 3 by 3 matrix that we want to solve to find out what the denominator is going to be on all of these variables that we're going to be solving for. But how do we do it? You know, last time we did that whole Seattle, Miami, LA to Maine. It doesn't work for this because that wouldn't capture up all the numbers. So we have to do something different, and this is a little trippy. Ready? What I'm going to do is I'm going to copy the matrix. It's a 1, 2, minus 1, 2. Then, okay, here's where it gets weird. I'm going to repeat the first two lines again. 2, 1, 3, 1, 1, minus 1. Okay, so I repeat the first two columns. That is just weird, but that's what you do. Okay, so I did it here, and I did, oh no, not there, sorry. Here, and here. This was the original 3, and then I did the next 3. Okay, so how do we multiply? We still follow that same sort of Seattle to Miami, LA to Maine, but with a twist. The first set of multiplications we're going to do are these 3. I really recommend a different color at this point. 2 times 1 times 2 is 4. The second one, and let me just do this so you can see how I got them. 1 times minus 1 times minus 3. That is minus 3. And then this one, and this one. That is minus 2. But all of these are being added because we know when we go from Seattle to Miami, we add, right? So I'm going to add all of those together. But now we have to do some subtracting, don't we? So I do the same thing. I start here in the bottom. And now I'm going up. And normally I would write my answer up here, but I put that note up here. So I'm going to go down here, and we're going to be subtracting all of this. 3 times 1 times 2, that's 6. And then minus 1 times minus 1 times 2. Those cancel. This is a plus 2. And then here, 2 plus 1 plus 1. And that equal, or it's not 2, it's not plus, it's times, sorry, 2. Okay, so I'm writing the pluses for all the ones that are going in that direction, and I'm turning all of these blue ones into minus, but then in between, inside of the calculation, I put the actual value that I calculate as I go. This is where the mistakes run rampant, so please be careful. Please, 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 please. 4 minus 3 minus 2 equals negative 1. And still I'm adding that, right? Because that is that. Inside of this reduces. This becomes negative, and what do I get in here? 6 plus 2 plus 2, that's 10. So the answer to the denominator, I'm going to switch back to green because we're putting these two numbers together. Plus minus 1 minus 10 equals negative 11. This is the denominator for all three variables, x, y, and z. We have to do this 3 more times because we have to do the numerator for x, the numerator for y, and the numerator for z. It's a lot. It's a lot, but we can do it. Let me pull this out. Here. Allow me to disrupt our filming for a minute. Okay, now I'll have the problem handy. This is my new solution for trying to see what's on another page. It's too hard to flip around a book back and forth, so I rip my pages out. Okay, so now that's the denominator. So now we need to go back, and for our x value, we need to, these are going to be all the numerators. So we'll start with x. We know that we're going to have a matrix like this, and we know that on the bottom is going to be our denominator. So I'm not going to write that all over again. I'm just going to put the answer right there. All right? Now we know that we're mentally imagining the columns here as x, y, and z. We know that we're solving for x, so we're not going to put the x coefficients in here. We're going to use the constants in the x column. 7 minus 2, 16. Okay, I took the constants. Now we are at the y column, and that's plus 1, minus 1. And then the z column is 2 minus 1, 2. You don't need to put the pluses. I just got carried away there. Okay, so now we've created the matrix, the 3 by 3 matrix that will allow us to find the numerator, but now we have to write it out so we can do the multiplication. So we have 7 minus 2, 16, 1, 1, minus 1. We copy it as it is, then we repeat the first 2 columns so that we can do that nifty multiplication. I know, it's weird, it's crazy. Now we do the multiplication. I'll show you again. We're still following that, Seattle to Miami, LA to Maine. If you live in a different country, then you can either check a map of the US, or maybe if you live in the US, you need to check a map of the country to see how those cities and states line up. But we're going to up, down, down, up, and we're subtracting. These numbers will be positive, these numbers will be negative. So let's start here. I always use my orange to go this way, and we're multiplying these numbers. This will be 7 times 1 times 2, 14. And then we do this kitty corner arrangement. 1 times minus 1 times 16, minus 16, and then this one. 2 times minus 2 is negative 4, and then this makes it positive 4, right? All of these numbers we will add, all right? And I'm just gonna go ahead and take it, simplify it. The 2 positives make 18 minus 16. That looks like oh, John doesn't show me that level of detail. This looks like positive 2 to me. All right, and now we will go from the bottom up, and we start in the leftmost column. 16 times 1 times 2, that is 32. And I'm gonna write these answers up here, as I said. Last time I had notes in the way, so I didn't, but now I will. Minus 1 times minus 1, that's positive 1, times 7 is 7. And then 2 times minus 2, that's minus 4, times 1, that doesn't change anything, that's minus 4. This will all be negative. That's a confusing step. The pluses and minuses are flying like crazy, aren't they? So this is plus. So this is 39 minus 4 39 minus 4 is 37. No, what am I saying? It's 35, right? Yes. So this equals minus 35. So now, to put these together, right, this is the sum of all of the ups, and this is the sum of all of the downs. So I put them together as plus 2 minus 35, and that equals minus 33. So this is my numerator. I know, it's so long that you think, what am I even doing? I don't even know. So now we can write x equals minus 33, my numerator, over minus 11, that's my denominator, x equals 3. Oh my gosh, did you ever think in a million years that it would turn out to be such a simple, cute little number? I didn't. I thought it would be, you know, some wacky fraction that would make us all cry. Okay, we've solved for the denominator. We know we can use that for all three values, x, y, and z. We did the numerator for x. Now we need to follow the same rules and go on and solve for y. Turning the page. And again, we're solving for numerators at this point. Y equals, we have to create the matrix, and then we're going to put it over minus 11 because that's our denominator, and that, there it is. Our denominator works for everybody. Okay, so again, we think about these columns as x, y, and z. This time we're filling in, we're solving for y, so this y column is going to be where the constant lives. The constants are here, 7 minus 2, 16. And then we fill in x and z, they're minding their own business, 2, 1, 3. And z is 2, negative 1, 2. All right, now we're ready to do our multiplications, but we better spread this out. Here's a shortcut you can do. Instead of copying the whole thing over again, I'm just gonna leave these three in the matrix, and then I'm just gonna add the two columns here. So now when I do my multiplications, I'm gonna ignore these lines. I just don't wanna have to write everything over and over again, right? We need to add the first two lines again in order to get our multiplications right. But now I've got everything I need and I don't have to recopy. 2 times minus 2 times positive 2. That, my friends, is minus 8. Okay, and these are all gonna be the pluses. Don't mind him. Next one, 7 times minus 1 times 3. That's negative 21. And next one, 2 times 1 times 16. Oh, that's 32 positive. Okay, I'll smush those all together and they will be the first part of my final calculation where we add these and then subtract the upward ones. All right, I want to simplify this. This is negative 29. So this is looking like plus 3 to me, right? Negative 29, yeah, so this is plus 3. That is my half of my matrix, half of my determinant. There we go. Now we need to go the other way. 3 times negative 2 times positive 2. That is negative 12. And these are all going to be subtracted, right? And now the next one, 16 times negative 1 times 2. That's negative 32. And then 2 times 1 times 3. That is plus 14. Right? I write my answers in here. This reminds me of what to do with them after I combine them all. Okay, I'm just double checking my calculations. I don't want to make a mistake in this. Make you all cry. Okay, so then we'll bring this together. This is, let's see, minus 44 plus 14. This looks like minus 30 to me. John doesn't show this step in the book, so I can't check it. 44. Yes, because if I combine these two, I get positive 2, and then positive 2 plus that would be negative 30. Okay, great. Now I'm ready to bring it together. It'll be positive 3 minus 30. Oh no, this one. It's minus 30. So it's negative 3 plus 30, right? This minus sign comes from this combination. So here, let me do this. Right? This is also a positive number, and I'm adding it. So let me write this a different way. This would be plus positive 3 minus negative 30. These two come together to make a plus, and my numerator for y is 33. So I put that over this. Look, John has done it again. Y equals 33 over negative 11. So y equals negative 3. Once again, John has tricked me. I would have guessed it would be a much more complicated number. Okay, so we've solved for x, and we solved for y, and now we need to go one more time and solve for z. And that is going to be that thing over 11, minus 11. That's our denominator. We're still keeping that. Here's our original system of equations. You know what? I never did this, and that just bothers me terribly. Okay, so this time we'll be putting the coefficients in the z slot. So let me just put these here. Remember, these are not part of the problem. They're just helping us organize. Z is what we're solving for, so the z column gets the constants, 7 minus 2, 16. And then we just copy the x and y coefficients into those columns. 2, 1, 3, 1, 1, minus 1. Okay, beautiful. Now we will, instead of recopying it, you can see in the book, let me just show you. This is John showing it to us. There's the matrix. He recopies the first 3 columns and then doubles up the first 2 again. What I'm saying is just skip this part and just add the last 2 columns here so you don't have to keep rewriting things. We haven't got all day, you know what I'm saying? Life beckons us. So I'm going to repeat the first 2 columns, 2, 1, 3, 1, 1, minus 1. Now we're ready to multiply. I always use orange to go down because it's getting warmer, and that reminds me positive. And I always use blue to go up because the weather's getting colder, and that means negative. That's how my brain works. Welcome to my world. 2 times 1 times 16 equals positive 32. I'm putting the plus on the outside. There's the 32. Then I do 1. I like to connect these like John does. I think that's cool. These 3, let's see, they make 6 negative. And then the last one, 7, 1, negative 1. That gives me a negative 7, right? These negatives will get combined with the other multiplications, and then we'll represent that as a positive number. So let's see what we've got. 32 minus 13 would be 19, right? 2, carry the 1, yes. So this is positive 19. We'll use that when we combine our 2 answers. Now we're going the other way. 3 times 1 times 7. These are all going to be negatives, but that is a 21. -1 times -2 times +2. Let's see, that's +4. And then this one's 16 times 1 times 1. That's 16. All right. So all of those go together. And this makes, let's see, this is 20. So this is -41. Right? So now to put these together, we start with this plus 19 minus 41. Hi, Grace. Grace gets to a certain point in the afternoon where she says, all right, I'm done listening to math. It's time to go outside. And we're going to go as soon as we finish this lesson. But we still have one more example, so you have to be patient. Good girl. Plus 19 minus 41 equals -22. Good girl. That's the numerator. She's getting really riled. And -11 is our denominator. John, he made it perfect. Z equals +2. So there are our three answers. They were 3, -3, and 2. So again, I like to see it like this, right? Ordered triple. And that, my friends, is how we use Kramer's rule, which uses matrices, to solve a 3-part system of equations. Did I hurt your brain? Okay, the last example, there's one little thing I need to cover after that, but let me do one more example. Good girl, Grace. Example 101.2 is the way John Moore commonly asks the questions. He makes a little, instead of having to solve for all three, he's just going to ask us to solve for one. Use Kramer's rule to solve for Z. And then he gives us the system. I'm going to put a Z in a big circle so I don't forget that I don't have to do all of them. 3x. So now here are the systems. Again, I like to put a 1 coefficient so that I don't have to think every time I try to grab that coefficient. Now, here's what's tricky. The second one is 2y plus 3z equals 14. And then the third one is x, I'll make it 1x, plus 2y equals 3. Okay, so this is a 3-part system of equations, and we have 3 variables, but they don't necessarily show up in every equation. So what do? We put in zeros. All right, and we're going to run our numbers just the way they are. I like to do the denominator first because, well, yes, because it's a good habit to get into, because the denominator is the same, and if you have any problems, you want to know right away. So I'm going to do the denominator. And I know that to do the denominator, I use all of the coefficients. I don't use these at all. So 3, 0, 1, 2, 2, 2. Double check, make sure that's plus. Oh, yeah, I know why. Because it didn't have anything there, so I didn't write it down. 2, 2, 2, and then 1, 3, 0. So we want to solve this matrix. In order to do that, we're going to have to repeat the first 2 rows. 3, 0, 1, 2, 2, 2. Time to go do that hot and cold thing. Good girl, Grace. She loves a good matrix determinant. The determinant is the answer to a matrix. 3 times 2 times 0. Oh, that got real easy real fast, didn't it? 2 times 3 times 1, that's 6. And 1 times 0 times 2, that is also 0. Those are our plus numbers, so that comes down to just plus 6. And now, good girl, Grace. I'm petting her with one hand, but if I stop to like change the, like I was just taking the lid off the marker, she gets really upset with me. 1 times 2 times 1, that is 2. I'm gonna write it down here. These are the negatives, so that's 2. 2 times 3, let's see, that's 6 times 3, that's 18. It's all positive. And then 0 times 2, make these little dashies, that's 0. All right, so we put all these together. This becomes 20, so it's minus 20, right? So then when we put the denominator back together, it's plus 6, that helps, minus, the number inside was positive 20, so that is negative 14. That's our denominator. Oh, Grace gave up and lay back down. Poor dog. Numerator, she's very patient. Numerator. Okay, we're solving for z. And we just determined that our denominator was what? Negative 14. So I'll go ahead and put that in, even though it just kind of gets in the way sometimes, but whatever. All right, let me pull my system out so you can see the numbers I'm choosing. Okay, I'm gonna write my little XYZ up here. That helps me remember which coefficients go where, but it is not part of the problem. Okay, Z is the column that will have the constants in it. 9, 14, 3. And then my X's will go in the X column, 3, 0, 1. And my Y's, oh look, 2, 2, 2. Instead of rewriting, I'm just gonna add the first 2 columns over again. I'm not gonna copy the whole thing like John does. Now I'm going to multiply in the warm direction first. These are the pluses. 6 times 3 is 18, and they're all going in the plus. That's kind of out of line, but work with me. 2 times 14 times 1, that is 28. Positive. And then 9 times 0 times 2, plus 0. Okay, so this all comes down to what? 46? It's positive 46, and then we'll be subtracting the cool numbers. 1 times 2 times 9. That's positive 18, but it's going with the negative in front of it. 2 times 14 times 3. Whoa, that's a big number. That is 6 times 14, that's 84, and it's positive. And then 3 times 0 times 2, that's 0. Okay, so this all comes to, let's see if I add that to that, it's what, 102? So this will be negative 102. So there's the answer there. Now I get to do my final calculation for the determinant, and I take plus 46 minus 102, and that will be 56, negative 56. I did that in my head. I don't even know how. Negative 56 is the final calculation for the numerator, right? I did my warm numbers, they're here. I did my cool numbers, they're there. I put together the warm and the cool here. That's my numerator. And then minus 56 over minus 14 is the value for Z. Let's see, this is 7 times 8. This is 2 times 7. So if I cancel those out, then it's 8 over 2, so z equals 4. And guess what? Lord have mercy, that is the right answer. We got the right answer before, too. Where is it? This is the right answer. John just shows the individual letters, the X and the Y and the Z. So let's go back and do those. That's correct. Y was -3. X was +3. Yes, that's what I got. Okay. I still like to see it like this. I like to see the answer all in one place when we're done. Okay. That is most of lesson 101. I just want to show you something that happens sometimes in a system of equations and makes it all fall apart. And we're going to look at these first with just two-part equations. And what we're talking about here are independent equations. These are good to know because they'll help you catch tricky situations as you're working these. Remember that sometimes we'll see a system where there is clearly a pattern within the coefficients. And we can see it here. 4 times 2 is 8. 3 times 2 is 6. However, 1 times 2 is not 42. So these match. They aren't equal, but they have a relationship. So I'm using this in a non-mathematical sense. They match. We can see a pattern, but these don't match. Now, what we could do, if we had all the time in the world and wanted to, we could solve each of these for y equals mx plus b format. And what we would find is that the slope is the same, but the y-intercept is different. And that tells us that we have parallel lines. Okay? So this is the pattern. The coefficients on the variables have a pattern, right? We can see that they relate to one another, but the constants don't. What about the other situation? 4x plus 3y equals 1, 8x plus 6y equals 2. Let's look at this system. 4 times 2 is 8, 3 times 2 is 6, 1 times 2 is 2. Everything matches. Again, I don't mean they're exactly the same. I mean that there's a relationship. That means that what we have here is the same line. And it's not that the slope is the same and the y-intercept is the same. The line is exactly the same. So it's really just one line. It's not two lines. So these are the two situations we want to be kind of on the lookout for. If we see this pattern between the coefficients on the letters, we want to look and see, do these follow the same matching? If not, then they're parallel lines. If they do follow the same matching, then it's really just one line. If we try to solve these with a matrix, the matrix will go to 0. And that's how we'll know there is a problem. And I'll show you John doing that here in just a second. He took the variables off those equations right here and he tried to solve them. And in both cases, he got 0. All right? So now what he's doing is he's going to show us that in a system of 3 equations, and I'm not going to write all this out because, well, yeah, I will. How do we recognize these same situations when we have a system of 3 instead of just a system of 2? Let us look. x plus 3y plus 2z equals 1. Okay. 3x, this is the system that I'm copying down, by the way, plus 9y plus 6z equals 3. Now, there's another equation, and I'll just write it down, but the first two tell the tale. We can see that these two equations are the same equation, right? Because if we multiply x by 3, we get 3x, 3y, 9y, 2z, 6z. Everything's multiplied by 3. My marker's dying. And so this tells us they're not even parallel lines, right? We know by our rule that this is the same dang line. And so we will not have an independent solution. That's the fancy word we use for this. Independent meaning like normal. And John does the extra heavy lifting. He takes this and he tries to solve it, and he finds that the determinant for 0, this is for the denominator, right? 131, 131, 394, 394, 262, 262, and then he repeats the first two rows. So he's solving for the denominator. The solution, the determinant, comes to 0. Do you want to put 0 in the denominator of this fraction to solve for x, y, and z? I don't, because you know what? The kingdom's already blown up and we don't need to make it worse. So that's proof that this system does not yield an independent solution. Let's look at the other one now and see what pattern that teaches us. Again, these are not examples. This is just John preaching to us. 2x plus, I'm going to put the numbers in, 1y minus z. Copy these with me. I know you are. I know I've got you totally sucked into this. I'm telling you, writing, taking notes is so much better than just listening, because it's so boring to just listen. Even to me. Oh, I forgot to put the 1 there. Work with me. Now, this one is weird. It's also not independent, but let me show you why. If you take these two, again, this is a system. Here we saw that A and B were related because if you multiplied A by 3, you would get B. This one is different because look what happens. If we add these two together, 2x plus minus x equals 1x. 1y plus 3y equals 4. Minus 1 plus 2 equals plus 1. When we add it, if we add a plus b, remember we can call this a, b, and c, it's the same as c. A plus b equals c. What? What? What that means is that once again, we have a matrix that goes to 0, and we have no independent solution. I wrote bigger this time. Okay? So, the reason it's worth knowing all of this is because if you ever notice these patterns, as you're looking at a system of equations that you're being expected to solve, you will know that something is up. The other thing you will know is that the matrix of the denominator equals 0. Or the determinant, rather, that's the proper word here. The determinant is the answer to the matrix. Determinant. The determinant of the denominator will calculate out to 0. That is another way of knowing you have these same situations, right? So you may not notice that when you're copying down the solution or setting up your matrices, right? You might just be cranking along. But when you get to the end of that calculation for the denominator and you find 0, then look back and see if you can recognize one of these patterns in your original systems. Oh my gosh, do you think we talked enough about Cramer's rule and 3x3 matrices? I think that's more than enough. So I believe we're coming back to these in the future, but for today, that's plenty. Thank you. Goodbye.